Hi, everyone. This is part two of our Big Data Project 1 presentation. Hopefully, y'all just watched Harrison's part 1, which was over the iris dataset. My name is Henry Burch, and I'm covering part 2, which is drug discovery. So on the next slide, this is a quick summary of what the drug discovery project is. So the dataset we are using is the DSC 43C8 dataset. And this is a dataset involving drug sensitivity. It has 555 cells across 98 drugs, where each row represents an observation or cell. And to explain this further, so let's see my mouse here. Every single column is a drug. So like AI car is a drug. This here, AZD 6482 is a drug. And the rows themselves are just the observations. And this is all the information I got. So because of this, I have a huge lack of domain knowledge. So I don't know what each drug is. I don't understand what these codes for observations meant. And for these values, I'm not sure if they are, I understand sensitivity, but I don't understand if it's dosages, if it's like a sensitivity scale. I really don't know. And I've looked online to find more information, but I couldn't find anything. So having this lack of domain knowledge really guided my approach to the project. So the first step was to pre-process the data by removing all possible missing data. Luckily, there was no missing data. So I just ran like is.na, is missing, all the possible things. There's nothing blank. It was great. So that step was easy. The next was to label cells into binary types. But you might be asking yourself, if I don't know what the values are or what the drugs are or what the observations mean, how would I possibly choose an effective binary type? That's the exact problem I was having. So what I decided to do was follow a very unsupervised approach, because unsupervised learning or machine learning is in summary the approach of when you know nothing regarding the data and try to do machine learning to uncover hidden patterns which you didn't know about before. So I use k-means clustering for this. And k-means clustering is an algorithm that aims to partition a dataset into k clusters, where k is a user-specified number. It does so by iteratively grouping data points into clusters based on their similarity, with the goal of minimizing the variance or distance within each cluster. And we already knew that we wanted to do binary types, as you see in the title of the slide. But I decided to do an inertia plot. And in summary, inertia is a measure used to assess the quality of k-means clustering solutions by quantifying the, let's say, compactness of clusters. It's helpful for selecting the optimal number of clusters and evaluating the effectiveness of the algorithm. And as we see, this plot on the bottom shows the inertia score on the left and the number of clusters on the x-axis. And typically, to pick a good number of clusters, you can use the elbow method, which is where, as you see, when you see the point suddenly improve less or get less, improve less, then you know that number of clusters is probably good. And what I would have picked from here is 2 or 3. So we can see that 2 is probably an effective number of clusters to use. Now, the next step here was to use PCA to visualize the data with the binary labels and find the outliers. So first, let me explain what we have here. This is a biplot where I applied PCA, which is a dimensionality reduction method. And on the x-axis, we have principal component 1. The y-axis, we have principal component 2. And every single data point where you see like DOK, GG75, or all those names, those are the observations themselves. And when they're blue, the blue represents cluster 1 for my k-means, and the green represents cluster 2. And what's good is that there is a clear separation, which initially seems like, oh, great, that's awesome, right? There's 2 separate clusters. However, when you look further into it and you really think about it, it looks like there's just simply a line drawn in the data, which probably means that my k-means algorithm just put a point over here on the left, put a centroid over here on the right, and said, let's just use those 2 to cluster them. And yes, that's an effective separation, But what does this separation line mean? Like, what about this line is special? That I cannot answer because I don't have any domain knowledge. And also, what's cool about principal component analysis is that I had 99 variables, and this helps me reduce it down to 2, which captures the most variance possible. And we can elaborate on that further later if needed. But these points here with the yellow triangle and along the right, those were highlighted as outliers. And once again, it's hard to know why without having domain knowledge, but this could at least be given to somebody who has domain knowledge, and they could probably translate it for us. Now here's TSNE, UMAP, and LLE, which are other dimensionality reduction techniques. And I think the point here was just to see what other methods would look like. And what's special about LLE is that it's really good at preserving the local linear relationships between data points. For TSNE, it's really good at preserving the pairwise similarities between data points. And for UMAP, it focuses on preserving both local and global data structures. Where this is interesting because PCA really focuses on global and has issues with the local. And WeSeek has a similar pattern here where there's decent separation, but it's hard to say why, or it's hard to see like a certain pattern. Like it's not like all on the left and all on the right. Sometimes they're overlapping, and it's just, I personally don't think there's much value to gain from this. And the next step, which is good, was to apply dbScan to the embeddings of the TSNE, UMAP, and LLE, and define their clustering information. And dbScan is a clustering algorithm used in data mining and machine learning, which groups points in the clusters based on their density, and it identifies regions in the data space where data points are close together while allowing for detection of outliers and noise. And what dbScan is particularly effective at is finding clusters with arbitrary shapes and sizes where it does not require the user to specify a number of k. It can tell you how many clusters it thinks there are and how likely it thinks that there are clusters present. And in the clustering algorithm, it requires that we have input the data, an EPS range, and a minimum samples range. And those are all inputted into the algorithm itself. And I wasn't sure which values to use, so here's a custom function I wrote actually to test every single possible combination of EPS ranges and min sample ranges. And I did this for all of TSNE, UMAP, and LLE. And you can see in the bottom is I set my EPS range there, my min samples range here, and I apply the function find best EPS min samples. And this tells me that 2, 5 is the best min sample, and that was the outputted score. Now, this was for TSNE, and I guess this is an example for LLE. For every single one, LLE, TSNE, and UMAP, my results were very poor, because what you see here is this is the outputted how many noisy points it thinks there are. So 0 would be non-noisy. In this case, 1 would be noisy. And it thinks that there are no noisy points. Noisy points are points that are separate and distinct and have something about them which stands out. And this basically says that it doesn't think anything stands out. It thinks everything would belong to one cluster. And to further that claim, let's look at the adjusted mutual information, which is on the bottom here, which is a score of 0. The AMI is a measure that quantifies the level of agreement between two data clusterings while considering chance agreement, and it is used to assess the quality of clustering results. So what we see is that dbScan is basically telling us that we think everything's the same. We don't think there are clusters here, which actually furthers our point from before about when in the PCA, on the PCA bioplot, we just saw a giant oval of points. And when we try to cluster, it just drew a line diagonally down the middle. And if you see that kind of thing in data, it's not likely that there are good clusters, and DB scan just kind of furthers that. So this is a big summary of everything I've found, but I'll just summarize it quicker than that. This is just so you can come back and read it later. But without having domain knowledge of a project, there really isn't that much you can do. It forces you to follow an unsupervised approach. But the thing about unsupervised learning is that you oftentimes don't know what type of pre-processing and feature engineering that has to be done in order to get the data into a form that's more consumable. So I took the opportunity to demonstrate why domain knowledge is so important. So to improve this project later, either I would have needed a big summary of what the data is and some information about it, or I would need to work with a medical professional who is very knowledgeable, where we can meet and he can explain the data and I can explain my data science knowledge, and we could come up with a solution together. So what we found here is that the data does not seem to have clustering, but there may be some pre-processing that can be done to determine what type of clusters are present. But I think honestly, my main summary is that domain knowledge is important. And next, you should watch part 3 to watch Guy's presentation of the patent section, which is part 3 of our project. Thanks for watching.